The Epstein drive is a hybrid fusion plasma ion drive. This video is not about how a fusion drive, plasma drive, or ion rocket drive works. Instead, this video is a focus on the specific design choice of continuous burn for sustained acceleration to simulate 1G. The distance from the Sun, which defines the center of our solar system, to Pluto, which defines the edge of our solar system, is calculated as having a radius of 4.545 billion kilometers. This is the number that I will be using to determine how the Epstein drive from the expanse universe works. To generate artificial gravity, the Epstein is designed to continuously burn to sustain a continuous acceleration. Acceleration is a rate of change in speed over time, which results in an increase in magnitude, whereas deceleration is a rate of change in speed over time, which results in a decrease in magnitude. I'm starting with the distance of the solar system to define the key constraint of the drive's primary design function. Most conventional rockets, which is the primary real propulsion system for space travel, reach their maximum speed, then power down. In this way, the craft continues under power until it reaches its destination. The Epstein drive is unique in that it is described as continuously burning or using fuel and remaining under power for the duration of the trip. This is done to simulate a force of 1G through the use of acceleration. To simplify, objects do not accelerate or decelerate at the same time. Any object under power will accelerate or decelerate dependent of any other object which is not under power. When an object under power accelerates into another independent object which cannot move out of the way, the independent object experiences inertial forces as it tries to remain at rest. These forces are calculated as G forces. The natural force of mass attraction of the Earth, which we use to measure the different density of matter on the Earth, is defined as roughly 9.8 meters per second. Every second, the surface of the Earth experiences a downward force of 9.8 meters. We describe this as gravity. If you pick up any real physical object and release it, it will move toward the center of the Earth in a straight line and come to rest when it collides with another independent object, to include the surface of the Earth in itself. This object is still physically in motion toward the center of the Earth, although it appears to be at rest. We call this fundamental understanding relativity. Relativity is the reasoning that objects in motion do not know that they are in motion unless they can check their potential and kinetic energy against another object within its proximity. I could continue with this line of reasoning for a long while, but instead, any question you have may be left in the comment section. We know the diameter of the solar system. We know the speed of acceleration required to generate a force to simulate 1G of mass attraction. What we do not know is how the Epstein drive does this, or if it's even physically possible. If we take the radius of the solar system, 316 billion, times it by 1.6 to get kilometers, we are left with a result of 505 billion 600 million kilometers. But this needs to be converted into meters to match mass attractions. So we add 3 zeros, which will give us 505 trillion 600 billion meters. Now that we have our figure, we need to divide 505 trillion 600 billion by 9.8 to get the total number of seconds. Why? We need to simulate the force of gravity. We are not currently focused on speed, just simulating the kind of acceleration required to simulate a force of 1 g. 51 trillion 591 billion 836 million 734,693.877. So I will just round this up to 51 trillion 591 billion 836 million 734,694 meter per second. This value is the number of spaces you will travel to generate a force of 1 g while accelerated. Each unit is equal to a distance of 9.8 meters. This is our meter per second. When dealing with acceleration, there is a distance value and a time value. You can travel across the solar system in 1 day. To do this, you divide 505 billion 600 million by 24 to get 21 billion 66 million 666,666.6. This value is speed kilometers per hour. In conclusion, the Epstein drive will be so slow as it would require a total trip time of 1,777,166 years to leave the solar system. No, my math is not wrong. A car traveling at 60 miles per hour does not take 1 hour to accelerate. A car accelerates to its maximum speed in a short amount of time, which is what causes inertial g-forces. If a car accelerates from 0 to 60 mph in 10 seconds, which is super slow, it will gain 6 miles per hour of speed every second. The Epstein drive is reaching a velocity. Once it reaches the edge of the solar system, a total speed of 35,280 km per hour will be reached, and it will take 505 billion 600 million kilometers and another 1,777,166 years after a flip burn to decelerate and come to a complete stop based exclusively on sustaining a 1 g acceleration. In the book and on the show, it is easy to see that the Epstein drive can reach g-forces close to 20 times the force of Earth's gravity. So it is safe to imply that the Epstein drive has sufficient overall power. Measured speed of the Epstein drive. For 1 g acceleration with flip maneuver in the middle, you are in the range below 16 days for any single planet in the system, and under 3 weeks when you are traveling maximum distances, like when Neptune is on the opposite side of the system to Uranus. Epstein drive is within the reach of fusion-powered rockets. The moon closest to Earth, 356,577 kilometers. Travel time at 9.80665 meter per second, decelerating halfway. 3 hours, 20 minutes, 24 seconds. Mercury closest to Earth, 77.3 million kilometers. Travel time 2 days, 1 hour, 19 minutes, 12 seconds. Venus closest to Earth, 40 million kilometers. Travel time 1 day, 11 hours, 28 minutes, 48 seconds. Mars closest to Earth, 65 million kilometers. Travel time 1 day, 21 hours, 13 minutes, 1 second. Jupiter, closest to Earth, 588 million kilometers. Travel time 5 days, 16 hours, 2 minutes, 2 seconds. Saturn, closest to Earth, 1.2 billion kilometer. Travel time 8 days, 2 hours, 20 minutes, 24 seconds. Uranus, closest to Earth, 2.57 billion kilometer. Travel time 11 days, 20 hours, 24 minutes, 0 seconds. Neptune, closest to Earth, 4.3 billion kilometer. Travel time 15 days, 7 hours, 52 minutes, 48 seconds. Pluto, closest to Earth, 4.28 billion kilometer. Travel time 15 days, 7 hours, 1 minute, 12 seconds. Leaving Earth to Moon, 12,024 seconds. 1 million, 1,779.326 kilometer per hour. Leaving Earth to Mercury, 177,552 seconds. 261,219.248 kilometer per hour. Leaving Earth to Venus, 127,728 seconds. 18,789.928 kilometer per hour. Mars, leaving Earth to Mars, 162,781 seconds. 23,958.570 kilometer per hour. Leaving Earth to Jupiter, 489,722 seconds. 72,040.872 kilometer per hour. Leaving Earth to Saturn, 57,097,440 seconds. 1,261.002 kilometer per hour. Leaving Earth to Neptune, 77,788,368 seconds. 3,316.691 kilometer per hour. Leaving Earth to Pluto, 77,785,272 seconds. 3,301.396 kilometer per hour. Conclusion. Based on my research and with all the data that I have provided, the Epstein drive works by having a primary main drive and a secondary efficiency drive. The efficiency drive, when powered, provides a continuous thrust that generates an inertial force of between 1/3 gram to 1 G. The primary drive is used to get a ship up to speed. What I'm attempting to convey can be illustrated by assigning some imaginary attributes to a custom ship from the expanse using a custom Epstein drive. The ship has a maximum speed of X and a maximum range of Y. The ship's primary drive has a mass acceleration, and its secondary efficient drive has a constant acceleration. If we remember, conventional combustion rockets travel under power until they reach escape vector out of Earth's gravitation influence. They then travel unpowered at a constant maximum speed until they arrive at their destination. The same holds true for the Epstein primary drive system. Only the Epstein secondary efficient drive system operates under continuous power. What needs to be understood about the Epstein primary drive is that It is designed to function at human tolerances. In the expanse, we see the stress of zero momentum acceleration, and the term hard burn acceleration is used quite often. These describe the function of the primary drive system. If our imaginary ship leaves Earth and heads to Mars with a maximum range of Neptune, it has both the speed and the fuel capacity to arrive at Mars within a specific time frame. To keep this simple, we will say that at its maximum burn, it takes 1 day or 24 hours for our imaginary ship to make the journey. If we take 65 million kilometers, then divide it in half to account for a split burn, 32,500,000 kilometers, we are given the range for a full burn of the secondary efficient drive. These keep the vehicle under constant acceleration to generate 1/3 gram to 1 g of inertial force.
We know the ship is going to travel 65,000 kilometers in 24 hours. So we can divide 65,000 kilometers by 24 to get its rate of acceleration per hour, which equals 2,708,333.333 kilometers an hour. But this is not accurate. If we take the literal description of how ships travel within the expanse, then one half of the trip has to be done as a deceleration. We shouldn't have to recalculate any values. We can assume that the average rate of 2,708,333.333 kilometers an hour is sustained for 12 hours and that the braking velocity will equal 2,708,333.333 kilometers an hour as well.
But what if the crew are not in any kind of hurry and they decide to travel from Earth to Mars in 2 days or 48 hours? This is where the fundamental comprehension of the Epstein drive comes into clarity. For this trick, the secondary efficiency drive will still keep the vehicle under constant acceleration to generate 1/3 gram to 1 g of inertial forces. But what changes is as follows. We know that the ship is going to travel 65 million kilometers in 48 hours. So we can divide 65 million kilometers by 48 to get its rate of acceleration per hour, which equals 1,354,166.666 kilometers per hour, the same as before. We still apply. The ship will travel at this rate for an average of 24 hours. Now the halfway mark takes twice as long to reach the overall acceleration of the ship's primary drive. Is much slower, but the efficiency drive remains constant. After 24 hours of travel time, the halfway point of 32,500,000 kilometers is reached, and the ship performs a split burn, then decelerates for another 24 hours at a rate of 1,354,166.666 kilometers per hour, arriving at Mars in a total travel time of 48 hours. The same map would apply for a ship that has a maximum speed of 12 hours from Earth to Mars. Like with a conventional rocket, the Epstein drive uses fusion power and its high specific impulse to reach a specific maximum speed to complete a journey in a set amount of time, safely accelerating to reach that speed so as to not overstress the ship or its crew. Once the speed is reached, the primary drive shuts down like a conventional rocket would, leaving only the secondary efficiency drive under power, which adds acceleration required to sustain the inertial frame of 1 g. Split burns deactivate the secondary efficiency drive, leaving only the primary drive under to decelerate the ship safely so that it arrives at its destination within its scheduled window. This application and functionality accounts for intercept vectors. if it takes the same amount of time for a ship to decelerate as it does for a ship to accelerate. In other words, if a ship traveling for 1 hour requires 1 hour to decelerate, then ships which are not scheduled for rendezvous with each other would never be able to do so. Instead, a hard or fast burn of the primary drive can bring a ship to a stop with an extreme deceleration. This is true for the Razorback ship in the Essence. It possessed the ability to accelerate and decelerate without performing flip burns, but the inertial frames within the ship were extreme. I could further this line of reasoning and continue to rant, but I would only digress from the focus of the topic. Thank you for watching. If you have any further questions, please leave them in the comment section below.